This is the second part of lesson 8.2. We're still talking about exponential functions, y equals a times b to the x. But before we talk about the next type of exponential function, we have to talk a little bit about the letter, which is actually a number, e. E, like the number pi, is irrational, which means that it is a never-ending decimal with no repeating pattern. So remember what we said about some of our other decimals that we might see. You might see something like 1/3. That can be written as 0.333 repeating. Other fractions or decimals that are things like 0.245, 245, 245, repeating. If there's patterns to them, they can be written as fractions, and we say that these are rational numbers. But e is not rational, it is irrational, so it's a never-ending decimal with no repeating pattern. I would like you to go to your calculator, please. And if you go to your calculator, you need to go ahead and, once it's on, hit second, and then use the ln key, second ln, which has the little e to the x up top. When you hit second ln, you should see e with a little caret parentheses. It's asking you what power you'd like to raise it to. I'd like you to just raise it to the first power right now. So go ahead and say e raised to the first, and you will get a decimal of 2.71828 ... This is the worth of e. So in the same way that you guys know that pi is 3.14159, etc., is pi approximately, you must know that e is 2.718. Okay, it is its own irrational fraction. So evaluate each expression to 4 decimal places. We're just practicing raising e to different powers. So, you know, if I say raise 5 to different powers, so 5 to the first, 5 to the fourth, 5 to the -3, on your calculator you can get answers for these, and we'll see what it equals. We're just doing the same thing, except instead of a regular looking number, we're using the number e. So this one on our calculator, raising e to the first power, is 2.718, and we have to round up that last one to a 3. Make sure that you're using the approximation signs, because since e never ends, we can never include all the decimal places we're approximating it. Then we want to have e to the fourth, which on our calculator should be 54.5982. We can do e to the -3rd, which, by the way, just so you know, this would be 1 over e to the +3rd. That is the same idea as e to the -3rd. So e to the -3rd is 0.04, this is a 9 and an 8 when it rounds up. E to the 1/2, things to a 1/2 power, by the way. If you remember, your radical thing is e inside of a square root. Remember, that's what the 1/2 means. So e to the 1/2 or e to the 0.5 is 1.6487 approximately. And then for this one, we shouldn't need a calculator. Anything to the 0th power is 1, and this one we do get to use equal signs for. So now that you've seen a little bit about e, and this is how you find it on your calculator, this is what it's worth, let's see why this is important. Why do we care about this number? It turns out that this number is actually very useful for us in something called the PERT formula. And we say PERT because it's P-E-R-T. All of those letters stand for something a little different. But this is something that we use to actually calculate money. And if you put money into a savings account and you let it sit for a little bit, how much will you expect to have after a certain amount of time? So you might already have a checking or a savings account, and you've seen this happen, that you put money in, you get a dividend at the end of the month or at the end of the quarter. It depends on the system. Most checking and savings are monthly, and different types of other intricate banking accounts might be quarterly or annually. But in order to calculate how much money you'll have at the end, you not only need to calculate how much you put in, which is called the principal, so this is your starting amount that you put in, but you also need to know how much your bank is going to give you back. So you have a rate of interest. This must be given as a decimal. So usually banks will tell you that they're giving 2.3% interest. You need to convert that to 0.023 as a decimal. And then we also need to know time, and this formula is set up for years. There are different formulas that talk about months and days and all that, but for us, we're talking about time in years. And then once you have plugged in your starting amount, your interest rate as a decimal, and how many years it sat there, then you get out the amount in the account at the end. So this is what you call an ending amount here. Now, this formula, A equals P ERT, is actually the same as your exponential formulas. So this is y equals a times b raised to the x. So your a value out in front is like your p value. Your base here is always e. So remember we just saw that e was a number. So e is always worth, this base here is always approximately 2.71812, It's always that number. You're not going to change the e. It's already set. You can change the principal, what you plug in, times that base, and then you have your exponent here is your rate times your time. So that's why we're using this formula that ties into this exponential idea. We're going to look at a couple of examples where you plug in different pieces, like your starting amount, your principal, the rate, and the years, and see how much you get out at the end. All right, so suppose you invest $100, so that's our principal amount, P, $100, at an annual interest rate of 4.8%, so this is 0.048 is our R, or our interest rate, compounded continuously. Now this idea that we're talking about in this formula only works for continuously compounded interest. We'll talk a little bit more perhaps later this year, and certainly if you take economics with Broman, the different types of compounding, but compounding simply means how often do you get back your dividend. So like I said, it could be monthly, yearly, quarterly. This idea is that it's giving you back a dividend every moment. Every single second, every single moment, it's giving you back a little dividend. It's a really nice deal. It's not something you get all the time, though, at banks. So, compounded continuously, how much will you have in the account after 3 years? So, T equals 3. So, we come to our formula, we plug it in, we say A equals P, E, R, T, plug in the pieces we know. A equals $100 times E raised to the 0.048 times 3, and we're going to make sure that you keep this in parentheses, because when we plug it into the calculator, if it's not in parentheses, it can come out kind of messy. We're going to have an approximation, because E is always going to make it approximately. So in your calculator, you type in 100, then do that second ln key to get your E, 0.048 times 3, close parentheses, and we should have 115.4. It says 884, but I'm going to round it up because it's money. I'm only going to 2 decimal places, so 0.49 cents. So about $115.49. If you don't plug in that 3 with your parentheses correctly, you might get an answer that says $314. That is incorrect. It is this one here. So if you plugged in and you invested 100, your interest that you earned is almost $15.50. That's a really nice interest after 3 years. All right, now we're going to do the same thing, except we're investing 200 at the same rate for 3 years. So P equals 200, rate equals 0.048, and T is still 3. So A equals 200, E raised to the 0.048 times 3. So A is approximately, plug this in here, 230.98. Again, round up that last one if you need to, because it's money. We're only going to 2 decimal places. So again, you invested 200, you earned $31 of interest. Pretty nice. All right. Something similar, this time we're investing 100, but our interest rate has now changed. Our interest rate is now 2.5, so a little lower, and it's still 3 years. So P equals 100, rate equals 0.025, and T equals 3. So A equals $100, E raised to the 0.025 times 3. Go ahead and plug this into our calculator. And we should have A is about $107.79. So the question that we have here at the bottom is which had more effect? A higher initial investment, or a higher P value, or a higher interest rate, a higher R? So look back up at our original problem here. Our original problem had $100 and the 0.048 interest rate, and we got 115. We changed the amount to $200, and we went up to here. And then we said, okay, let's go back to the 100, but this time the interest rate is a little lower than it was originally. And what do we get here? So we can see that with a low interest rate of $100, we get $7. We raise the interest rate up here, and when we raise that interest rate, we got almost double the interest back. We went from 7 something to 15, so almost twice as much interest. Versus if we had $100 versus $200 and they both had the same interest rate, we doubled the interest here as well. So which one had more effect? That's kind of hard to say. They both had an effect. They both doubled. So it depends on the problem. They both increased the P amount, the principal. To say which one specifically had more effect, this one went from 15.5 to almost 31, so that's about double. And that would make sense because we double the 100, the 200. 0.025 to 0.48, and we went from 7 point something to 15 point something, almost also about double. So they're actually about the same in this case. All right, now you're ready for your homework.